All right, thank you for tuning into my talk today. My name is John Wendeborn. I'm a third-year graduate student at Boston University, and today I will, as the title suggests, be telling you about millimeter variability of FUor objects. So first, brief overview of the talk. First, I'll talk about what an FUor object is, as well as why they're important, why we care about them. Then I'll go into a brief overview of our small study, our sample, what instruments we use, etc. And then finally get into the discussion of the results, the variability that we saw, why we think we may have seen it, and its implications for FUor objects, as well as potentially star formation in general. So first, what is an FUor object? Well, an FUor object is a class 1, young, low-mass protostellar object. It's surrounded by an actively accreting disk, which in turn ejects a wind. And outside of this system is an infalling envelope consistently dumping mass onto the accretion disk. But how is this any different than any other young stellar object, like a T-towered object? Well, FUor objects are characterized by a rapid, large brightness increase, typically on the order of 4 to 6 visual magnitudes. And this brightness increase is thought to be due to accretion, where the quiescent accretion rate of 10 to the minus 8 solar masses per year increases about 10,000-fold to 10 to the minus 4 solar masses per year, depending on the object. And this accretion outburst can initiate within 1 to 3 years, but it does vary from object to object, and it can also last for 100 or more years. Again, depends on the particular object. And so why do we care about them? Well, it's thought that FUor objects, outbursting episodic accretors, are a potential solution to what's known as the luminosity problem, whereby the quiescent accretion rates, like I mentioned, of 10 to the minus 8 solar masses per year for these low mass objects implies a formation timescale of a solar mass type star of about 10 to the 8 years, whereas we actually see stars form within about 1 million years. So there's clearly a disconnect there. And the potential solution is episodic accretion, where an object accretes a whole bunch of mass all at once, as in the FUor object. And you can see here, these spikes in the mass accretion rate, these are all FUor events. So it is thought that FUor objects do undergo that young stellar objects undergo multiple large accretion events or multiple FUor eruptions. And it's also thought that 10% or more of a low mass star's total mass can be created in these FUor eruptions. And so you may be wondering what causes these outbursts. Well, it's thought to be due to some combination or individually of magnetorotational, gravitational, or thermal instabilities. And these instabilities may be triggered by companions, but the outburst mechanism is as of yet undetermined. Either way, FUor objects necessitate a large disk mass in order to sustain, or in the case of gravitational instabilities, trigger the instability and trigger the accretion outburst. As I mentioned, the events can last for up to 100 years, and the accretion rates can be 10 to the minus 4 solar masses per year, or equivalent to upwards of 1% of a solar mass during an FUor outburst. So the disks need to be fairly massive. And that's what we generally see. Most observations using instruments like ALMA at millimeter wavelengths find that the disk masses are quite large, on the order of half a solar mass in some cases. But in other cases, we find quite low disk masses where the disk mass is not quite large enough to trigger these outbursts. So either way, we need more and better disk mass estimates of FUor objects in order to better ascertain what the outburst mechanism is. However, this is complicated by the fact that we've seen millimeter variability at 1.3 millimeters in 2 FUor objects. And the magnitude of this variability is about 25 to 60%. And it's at 1.3 millimeters, which is often used to estimate disk masses. And this variability hinders a reliable disk mass estimate. So we can't properly understand the FUor outburst mechanism until we fully understand this millimeter variability. And as of yet, we don't know a clear cause for this variability. So we thought that we wanted to better understand this variability, so that was the intent of our project. So we looked at 3 objects, all in Cygnus, 2 of which I just showed previously have shown signs of millimeter variability. We used the NOEMA interferometer at 2.7 millimeters, and we observed these 3 objects in 3 epochs, and we obtained a one more epoch from 2014 of one object, B1735 Cygnus. And so what did we find? Well, not a whole lot, except we find a roughly 80% increase in the 2.7 millimeter flux of B1735 Cygnus from April 2014 to June 2017. And so what might be causing this? Well, our first thought was millimeter emission traces the dust in the disk. And so we thought maybe there is a mass increase in the disk, but the 80% flux increase implies a 0.3 solar mass per year infall rate from the surrounding envelope onto the disk, which is completely unreasonable. It would imply that the surrounding envelope would dissipate within 50 or so years, which we don't see. So material buildup alone cannot explain the flux increase that we see. And as it turns out, neither can stellar irradiation. So the idea here is that a brighter star heats up the disk, which then increases the amount of millimeter flux. Basically, the disk's overall temperature rises. But we don't see any corresponding flux increase at shorter wavelengths, in this case, near infrared wavelengths from WISE. You can see here there's really no overall change in the flux of B1735 SIG between 2014 and 2017, at least not sustained on the 6-month cadence of WISE. And so from this, we can assume that increased stellar irradiation also alone cannot explain the flux increase. And so one thing we thought about was free emission. So first, just a brief summary of what free emission is and how we can see it. So accretion ejects a wind in these types of objects, and in the wind, there is a component of free emission. It's often seen in these highly accreting low mass objects. And so using this prescription here for the spectral index, without free emission, the spectral energy distribution, the SED, would have a slope of about 2 to 3, as shown here. And this is quite common in protoplanetary disks. But when free emission becomes significant, the spectral index, or the slope of the SED, shallows and tends near 0. And for purely free emission, the slope is about -0.1 to about 0.6. So we looked at the spectral index for some of our data, and in 2014, the spectral index was assumed to be, was estimated to be between 1.7 and 2, which roughly puts it in line with most protoplanetary disks. We were unable to obtain a spectral index for our June 2017 observations, but we were for our June 2018 and August 2018 observations. And we find that the spectral index was lower at about 1.3, 1.4, which could imply that free emission became significant in this object due to some previous accretion outburst. And I will note that these error bars are quite large. However, we do believe that free emission is a likely explanation for the flux increase that we see. And so what does this all mean? Well, if the free emission increased, well, then disk masses obtained via millimeter fluxes may be overestimated. The free emission would be contaminating the dust emission, leading to inflated millimeter fluxes and therefore inflated disk masses. And so if we can't get a better understanding or a better constraint on this free variability, this millimeter variability, we can't constrain the disk masses of these objects very well. And so more work needs to be done to better understand the millimeter variability, this free emission, so we can better understand the FUor outburst mechanism. And with that, I'll leave you with a quick summary. And of course, please reach out to me with questions or comments about this work. This is, I do have a paper on this work, so you can see more details there. Email me or visit my website, johnwendeborn.com, and thank you for watching. Whew.